Dr. Jerry Smith. Thank you very much for attending the June version of AI in a Day. We've gone through several of these to date, which has been pretty exciting between Arnie and I. And if I can get to my slides here, between Arnie and I, who is our lead data scientist here in North America, and myself, I manage analytics and data sciences. So you'll get a chance to learn a lot about both of us as we go through. Today we're going to continue on with our journey in understanding the role that AI plays in your ability to change the world, and that's where we start. Our goal today is to give you 3 primary tools with a little bonus at the end. 3 primary tools that will enable you to change the world, not just observe it, but to literally change the world. And we're going to do that by doing some hands-on stuff. Today's sessions is different than the previous ones. So if you attended those, what we're doing on this one is this last bullet point, not the closing, but the optimized student performing using deep. We're actually going to optimize today. Before we didn't have time to do it, we didn't have it set up, but today we do have it set up, so we'll do that for the first time. We'll actually use evolutionary computing to do that. So today, we're going to set up a lab. We're going to get that going. We're going to talk about artificial intelligence perspective, a lot of discussion, so we set the context. And you are going to see some things that you probably haven't heard before here. And it's designed to help us get off of our X and take a step forward to change the world, right? And these things are done to challenge your perception of what AI is, right? If you go, oh, I've heard that before, chances are I'm not saying it right. Because what you should say is, I never thought about that. That's interesting. If I did that, could I advance our business? Could I advance our cause more along the lines of changing the world that they live in versus just reporting on it? So we're going to go through that perspective. We're going to walk through an example with breast cancer. We're going to walk through causality and building models. It's going to be quick. It's going to be fast. Your fingers will not be on the keyboard. It's just to say, hey, in 14.5 minutes, here's how you can go from 0 data to hero a digital surrogate quickly. And that's the idea. And it's through the whole process. Then we're going to jump right into a causality lab. We're going to talk about student grades. In there, we're going to get into machine learning after that, after we get the causality done, and identify what things are causing student grades to go up and down. And by the way, some of the things you're going to go, duh, I know that. Other things you're going to go, I never thought about that, right? That's the idea, right? Our world is to always say, I never thought about that. If we can look at a problem and begin to explore it and discover it, understand causality and build digital surrogates and go, I never thought about that, then guess what? We will change the world. You can't change the world if you're doing everything that everybody else thought about. You're just going to participate in that world, right? We'll then get into machine learning. We'll hop over to Microsoft land, and we'll actually go through and do some machine learning work and building out an actual digital surrogate based on our causal model. And then lastly, we're going to take that model and find the optimal conditions of which student performance can be achieved, right? And then we'll close it up with some observations and stuff like that. And that's what we're going to do. So where do we start? We start here with the labs, right? And I'm going to turn this over to Arnie in just a second, who's going to walk you through setting it up. By the way, he and I are kind of laughing on the sideline. We've done this several times so far, and every time we've done the labs, we've always set it up so that we're running on something like a 1 CPU, 1 core system with like 1 kilobyte of memory. For some reason, we've set it up like that, and it takes us forever. I think today we got the quantum computing version of the environment set up. So we're hoping, our intent, hope's not a strategy, but our intent is to see a lot faster responses for our work so that we can move through this at a more reasonable pace, right? So you'll see this link here, which will be in the questions. You can see an activation code. We're going to launch the lab, do some environmental stuff, grab your names, go to the portal, kick it off and stuff like that. So for right now, I'm going to turn it back over to Arnie, who's going to walk you through that process. All right, Arnie.
All right, let me go and share. Come on.
by the way, that's there. Sorry.
All right. Morning, everyone. All right. So the first step we do is to click on the link that we have posted. You should have had an email. Jerry showed the link in the slides. And then I also put it in the Q&A question. So the first thing you do is to sign up. You go into the registration page, you sign your name in, email address, and in the past we've got some feedback saying that the organization you will have to enter AgileThought. So go ahead and do that and put in AgileThought. It should pop up with a drop-down list and click on AgileThought. Once you hit register, there's going to be another page that says Launch Lab. And then once you click on that, you give it like, I don't know, 10 seconds or something, and then you will get this page here. In the past, they would just automatically go here, but now the lab people have actually upgraded and jump right away into the this page here, the environment details. So where we're going to work in is to just pretty much just use the username and password for our Azure cloud environment. So the first thing you do is just click on the username, and then we go to portal.azure.com, and then you'll be able to log in. So I already did that. Let me go back to the main page. So if you already have an Azure environment that you're working in, you would then have to go in here and then go hit sign in with a different account, and that's how you would enter it. Then the next step is to find all the resources. So that's this icon here. Click on those. And so the lab is already set up with all the services that we need. But what we're going to focus on today is to work on AI in a day. So we click on that. And then we hit the Launch Studio. So this will launch our Azure ML Studio. And then once you hit that, it'll pop up a new window, and we'll be in this environment here. So in the past, we've always started here with our compute environment. And this is what Jerry was saying, that we always start with like the cheapest and the kind of common door equivalent compute. Everything takes forever to run. So they already now set us up with the compute instance. So the compute instance is to run our notebooks. So we need this, and this has already been set up for us and ready to go. The compute cluster is what we're going to use for when we develop a ML model. So this is the default one that is set up. So we're going to go ahead and add a new one and just have a little bit more compute optimized. So let's go ahead and click on this one and just give it a name. And we'll create it. So let's put in like 4 nodes. And then we'll let this, we don't need this until later, but we'll just let it nodal while it's set up. So since we now got our compute instance for our notebooks, let's go ahead and jump into the notebook session. So on this left pane here, we got it's 3 sections. This section here is what they call the authoring. This is where you develop all your stuff. So your notebooks, your AutoML, and the designer. Then the second pane here is the second section of the pane is more about the model management, the data, and so forth. And then the rest is the compute and your data store management. So let's go ahead and go into the notebooks, the top one here. So you notice that there's some notebooks already put in here. So these are now the default that came with the compute instance that Microsoft set up. We're not going to use those, so just go ahead and ignore those. You should have a zip file that we already sent you. So let's go ahead and upload some files and folders, and then so we can get up and running. So let's go ahead and upload the files. So we are going to work with now our June data sets. So let's go ahead and upload the 4 files here. They end with the IPYNB, and those are notebooks extensions. So if we upload those, we trust the content, upload it, and then we're going to upload our data sets and figures. So let's go first start the upload of the data sets. Again, we trust it. And then finally, let's upload some figures so our notebooks will actually look nicer. All right, so now that we have this up and running, let's go ahead and use the time and import some of the, import some of the libraries we need. So by default, Microsoft has already uploaded some of the main libraries, but we are going to be using some custom libraries that are needed for this workshop. And I like to work in Jupyter Lab. So there are several options you have when you work in Azure ML. You can work in their VS Code, Jupyter. So this would be your normal Jupyter notebook, and then the Jupyter Lab. And then also by default, we're in this Azure notebook right here. So you can see that here. But we're going to go ahead and kick off edit in Jupyter Lab. We have to trust this, hit continue. It opens up a new window, and so we'll stay in that area. So give it a minute while this loads up, and then we'll stay in this environment. And this is where we'll see all of our notebooks, all of our data, all in one here. So let's go ahead and start by, like I said, we need to install some of the libraries. So let's go ahead and install those, and then we'll get it back to Dr. Jerry. Yeah, go ahead.
Hold on. For those who don't know about, who maybe not use Jupyter notebooks or notebooks, when you click on that, what did you do to get that to run?
Sorry. So use your mouse or scroll, however you want to do. You scroll down to this cell here, and then you click inside the cell and hold in Shift and hit Enter. That's going to execute it. You can also right-click on it, and it should be probably not a run there. So you can also go and hit the Run Select Cell, or you can go and hit the Run button here. And there's, I think, one more way to also click on it. But anyways, Shift and Enter is like a most common way to work with these. And now that we've installed it, which actually took a lot faster since we actually have a lot better compute now. So anyway, I want to just kick it back to you, Dr. Jerry, then. If there's any questions that came up while I was walking through this, let me know.
All righty. Just clicking over here to go live. That was much faster than last time. So here's where we are right now, right? We've managed to get your environment up and running. And of course, send live. Why didn't that go over live? That's interesting. Like that. I'm looking for the presentation. It's the only thing I know how to do. Let's see here. Send live. Interesting. Hey, Arnie, do you see the presentation, or do you see your workshop?
No, just my workshop. I had to go click on the pane on the left and then down on the bottom to select your.
Yeah, that's what I did too. I did that. I did send over.
And I don't. Let me go and stop my sharing. See if that makes a difference.
That'd be awesome. That's different from last time. Last time we were able to, there we go, there's me. Interesting that we cannot get this presentation up. So I'm going to stop sharing, and I'm just going to go back here and share again the old-fashioned way, which is here.
Well, that one thing is for sure, you know it's a live event when this happens.
Yeah, it's a live event when you can actually have all this sort of stuff. And let me just see here, where is what I'm looking for. I'm going to go ahead and share this piece and get rid of all this. Oh, look at that, just a huge mess. Let's see if I can get rid of some of this stuff here. All right. All right, so now at least we have the presentation. That was a long way through it, very different from last time in our world. So what we've done is we've got the environment set up, we've got the compute, we've got things installed. Now, typically this is where I get a chance to spend a lot more time because we're waiting for everything to go, but today we can make it go just a little bit quicker. A little apple pie and motherhood here. If you don't know, AI is a big market, huge. The issue isn't that it's a big market and growing. The issue is what are people looking for next, right? Back in the 2018 era, they were looking at doing, these deep neural systems, and modern analytics came after that. And companies are dedicating workers to now monitor these neural systems for performance, right? That happened late in 2019's early 20s. A lot of data science tasks were starting to be automated in this space. The key shift between the prior to 2020 and today is this focus now on revenue performance metrics, right? Because artificial intelligence is artificial to what? It's artificial to human intelligence. Most important assets in a company are human beings. Those human beings, we have a primary measure of effectiveness for an organization. I think we all know that is. Your CEO certainly does. And that's the revenue per employee, right? And so we try to maximize that number as a way to, help the market understand how well we're doing. And so now we're looking to say, can we actually drive revenue through the growth of this artificially intelligent capability, right? How much revenue per AI are we actually achieving? And then here, as we move into 2020, and certainly accelerated by the COVID situation, most of the jobs that are non-routine tasks, they're going to be relying upon AI to do their job as a function in that space. So pretty cool stuff. This is a slide I like, not because it has a lot of pretty moving bars and graphs in there that look fairly complicated, but the piece that I want you to take away is the one on the left-hand side, which says this: if you're not applying AI, and it's a competitive space, and your competitors are applying artificial intelligence, if you don't catch up and you become a lagger or a late majority person or company in this, you will go out of business, right? Artificial intelligence is a asymmetric, exponentially differentiating capability. And what we mean by that is you can't play catch up with intelligence by learning what that intelligent characteristic was a year from now. Why? Because the person who's applying it, who's achieving the prescriptive, and the person who's changing the world with their AI is going to exponentially outpace you in your world. And that could lead to an extinction level event. And that's what this data actually shows us in terms of those that are first runners and those that are laggers, and how it affects their organization.
And
right?
I think Elon Musk had a quote, and he said, if your competitor is racing towards AI and you don't, they will crush you.
Absolutely, absolutely. Again, two characteristics, man. It's asymmetric, which means I can apply it and you don't have to, right? By the way, things like terrorism are asymmetric threats, right? It's a very interesting field of study in terms of chaos theory. And it's exponential and highly nonlinear, right? Well, exponential is nonlinear, so it's a nonlinear environment that grows exponentially, right? And what we mean by that is every day that goes by, the gap doesn't get separated by twice the amount, it separates by more than twice the amount. And you get to a spot where you just go out of business. And we see that with a lot of different companies today. I love Elon Musk too. All right, so there are a couple slides that we're going to ask you to take away and probably use. This is or 3 slides. This is the first of them. Call this a circle of life. This is just an AI-driven digital transformation view. We're going to go through the first 4 steps today. We're not going to do step 5 and 6, and you'll understand why in just a second. And we're going to apply, in terms of those steps, we're going to go through various aspects of data science, which is going to take us from data engineering. We'll do a little bit of analytics, a lot of data science on there, and then machine learning, and of course artificial intelligence. And what we like to do is we break at AgileThought, we break down artificial intelligence very differently than most organizations. Marketing has done a wonderful job in confusing the world on what AI is. AI is artificial intelligence. It's artificial to humans, right? Human intelligence, HI. And the important aspects of AI are, it's in the prescription, and that is human beings are brought into organization to make decisions, right? To actually make decisions and do things. To do what? To change the way the company is doing business, right? To make a difference today that manifests itself tomorrow, right? That's what human beings do best. That's why you're hired. So artificial intelligence is a prescriptive activity. It's a step 4, which we'll get to. Machine learning, however, is all about predicting the impact that a change will have in the future. So it's all about time and space predictions. And then data science, of course, is looking at all that data and saying, what is this telling me, right? You know, when we think about the average IQ of a person out there, we don't, every time we think about that, we don't go and survey, 385 million people in the United States and then take their IQs and divide by that number. We don't do that. What we do is we survey it once, we model that information, we use that to then go forward. And of course, we have analytics, data engineering, data. So what's the cycle of life cycle? Well, it starts off with number 1, which is the debris of human activity, right? And that's data. I often ask the question in almost all my conversations for first contact, when you and I get together and we're trying to sort of lay the playing field out, is I ask, what's data? Right? If we're going to spend all these millions of dollars, tens and hundreds of million dollars on getting it, storing it, and leveraging it, we should at least have an understanding of what it is, right? And a lot of folks say data is a binary number. It's a hexadecimal code. It's stuff that's stored in systems. But data, at the end of the day, is the results of our human activity, right? It's because of us, not in spite of us, right? So all the data that's in your system, your revenue, your margins, your customer satisfaction, is representative of some sort of human activity. If I wanted to increase your revenue by 10%, I just don't go into your system and multiply your revenue numbers by 1.1. If I wanted to increase your margin by 30%, I don't multiply your margin numbers by 1.3, right? You just don't do that. Now, if you do that, you end up going to jail, but that's a different story, right? So what we say is, if you want to increase revenue and improve performance, we actually have to do something with our customers, right? We have to do something with our employees, and therefore change their behavior in order to change the data we collect. So we do that. That's step 1. Step 2 is to say, hey, not all data to our business problem is of concern to us. We have to store it all, but not all of it is causal to an outcome. If our goal is to change the world, not observe it, right? Change the world, not observe it. To change the world, not just report on it. If that's our goal, then we got to figure out what of that data is causal. What we mean by that is, if I force a change in that number, the actual world will change because of it, right? It's a causal relationship, not a correlation relationship. And then finally, once we have that causal data, we can build a digital surrogate, a special predictor, the inputs of which are the causal and the output of which is that business concern we have. So we have the inputs, we have the outputs. That predictor model is a special term called a digital surrogate. You hear a lot about that these days. A lot of people do a very poor job in defining it. But the idea is, this is an entity that reflects and respects, right, the environmental characteristics and performance characteristics of the real thing, right? And the only way you can do that is by making a causal predictor in terms of your digital surrogate. With that, and as I say, with that, and another $1.25, we are only halfway to a Starbucks coffee these days. But just because we can predict tomorrow adequately, it doesn't mean we can change tomorrow. So what we now have to do is we have to say, under what conditions, under what inputs of that digital surrogate will we achieve our optimal output, our optimal revenue, our optimal margin, et cetera. So how do we do that? Well, a lot of people think that's by building another model, and it really isn't. It's more about looking through the entire search space of the inputs in that model for the maximum results, and that's just that's a global search characteristics, and that's what we're going to talk about differently today than others. We're going to talk about how do you optimize those models using evolutionary computing and some other things. Once we have those inputs optimized, now that we know A, B, and C, what they have to be in order to maximize our business benefit, we then go implement them, right? And I'll just put a small plug here. A lot of people will take those inputs and struggle to implement them in their organization. Internally and externally are two different environments. If you're going externally, you need to take those things and go to your marketing and sales organization, and they create programs, awareness programs, and sales characteristics that then motivate people's behavior. We usually like to start with psychologists and sociologists, right? Because if debris is the data of human activity, or data is the debris of human activity, sorry, if data is that debris, and we now know under what conditions that data has to change in order to maximize, what we want to do is ask a psychologist, how do I change, how do I motivate the individual? What kind of behaviors do we do, and what kind of programs need to be put in place that marketing and sales? And then when we talk about group dynamics, right, going viral is a group dynamic, a sociologist is really good for that. So in the world of tomorrow, step 5 is actually 2 new resources. The psychologists and sociologists will participate with sales and marketing in order to help you establish those programs that will in effect achieve the inputs that you need for the optimized model, from which is causal, from which came from the data, so that their behaviors change. And what happens? Data changes, wash, rinse, and repeat, right? The next slide whoops. I think the next slide, real quick, is, and I'm going to cover a couple of these slides, and then we're going to get back in to actually do the demonstration here. This is the next slide, which is useful, right? This is it's a busy slide in the sense that it shows sort of a flow approach. Today we're going to be starting with the data sources. We're going to bring it into our environment. We're going to map it into a common area. We're going to look at causality. Today we're going to do a Compellon or a causal next version of that. Compellon's another tool and technology we use. You'll hear more about that later on during the month when we do another presentation with them, but we'll do a causal next. Why? Because we can upload that into Microsoft land. From there, once we have those models, we then build machine learning, whether it's a bespoke version of it with like we're going to do today, or it's actually a product of the platform we're going to use. We containerize it in sort of a step 2 in a Docker approach, and then we create a front end microservice out of that that's integrated into your application. Remember, and this is a plug for an upcoming podcast, AI is a feature. It's not an application. We'll talk more about that. We then take this AI capability and plug it into your overall application, and then wash, rinse, and repeat the process out of all that space. This is used by more of our customers than anything else, right? This is what we call our capabilities model. People often ask the question, and again, I'm just laying the context here. Typically, it's we need to do this while we're waiting for things to upload and consolidate, but this is probably already done by now on your side, and then we'll get into the actual work. When you think about what data science is and machine learning and AI, we talked about that. But what are the things that we do? And this is a capabilities model. It goes from the left, which is your data, your enterprise data, your IT data, your open source data, right? It goes from that data sources and builds through a staged version until you get to the very far side, which is your insights and your actions, right? Your insights and your actions. And each of these boxes represents one of many sort of capabilities that a data science needs to bring to the table, or a data engineer. And they're color coded accordingly in terms of the level of the expertise you have. And then on the very far side, you see sort of some of the tool sets that are often used, not exclusive. You won't see a lot of sort of high-end enterprise level tools in there. This is sort of the practical data science tools. But the idea is a simple one, where we can then take the data that we're going to be using today from UCI. If you're looking for data, go to the UCI repository. There's always a data source there that is, if not the data you need, a very close proximity or a digital surrogate for your data that you can use. We're going to be taking those data sources, harvesting them through textual harvesting. We're going to do a causal analysis. here on them. We're going to do some descriptive work and classification, do a couple decision trees in there, some machine learning work, and then optimize it, which I need to actually update the graph on that because we didn't do that last time. So we will do an optimization on that particular. So this is a pretty interesting way to think about your world. It doesn't guarantee success, but it does guarantee that you won't not think of something as part of the planning activities for data scientists. I ask most of my data science colleagues when they start a problem, well, how do you plan on addressing it from a data science? And it's a pretty ad hoc process these days. There's no systematic way. This is one of those ways that just allows us to systematically make sure that we have the right components in there. Today, our partner is Microsoft, and we're going to be using their environment, which I love, right? And the little red dots here represents the things that we're going to be leveraging. We're leveraging Jupyter and some stuff in sort of scikit learning, and we're going to be in their machine learning environment. And it's all going to be CPU based. It's a great environment. As a data scientist, I don't worry about these things. I just worry about data and doing the modeling. From a layered perspective, we are going to be working in the notebooks. We are going to be doing our data sets and creating it. We'll see how that works, and then our training, and then work compute and our cloud stuff's all going to be in the Microsoft land. And then I think our last environment here, before we get into a quick walkthrough of a demo on what you're going to do today, is to realize that we're going to spend a lot of time in the visual environment as well, which I love. As much as people love Python, human beings are not meant to communicate that way. We're meant to be visual in nature. That's why our brains are the way they are. We're a very visually oriented species, and so having an ability to leverage something like Microsoft's Azure visual environment, it will speed your way to development. Okay, so a lot of stuff today, a lot of stuff. I hope that was interesting to you. Right now, we're going to do a walkthrough. This is your fingers aren't on the keyboard. I just want you to focus on the screen. Arnie's going to really quickly bang through stuff, and that we will then slow down to in the next sessions. Right? We're going to start with cancer malignancy, and on the screen here, you'll see that we grabbed the data from the UCI repository. It's fairly old data, so one can often ask the question: is there anything we can learn from looking at old data? Absolutely yes. Right? And what is our goal here? Our goal in this repository is to build a better classifier. Right? Is to say, listen, if I can get these fine needle aspirated slides underneath a microscope, could I do a better job at predicting whether this cell is malignant or not? Well, this work has already been studied. The science has settled on it. So we won't make science in terms of, oh, look it, we're able to predict it. But what we're going to do is make science in terms of understanding what are the causal drivers for that prediction? What are the ones we have to focus on? And then once we understand the causal drivers for that, we can begin to ask fundamental questions. What causes that characteristic from a genotypical, phenotypical, or nutraceutical perspective that we can treat against? And we'll have a little conversation on that as well. So I'm going to turn it back to Arnie, who's going to quickly walk through this process again. Less explanation, more about what we're doing here so that you can see how we take the data, bring it in, do the causal, create the model, and then create the causal piece of this, and then move forward. Arnie?
All right. Thank you, Dr. Cherry.
Yeah. See, yours worked. That's interesting. Mine didn't.
All right. So this is where we left off last time. We were installing some library. Causal-Next is our causality library, so that's why we needed to install that. But since we have finished those, we have to go and clear the kernel or restart it. So now that the compute that we have working behind the scenes, now they have Causal-Next running on them, and then we needed to restart it to make sure it's got updated with the libraries in place. So instead of running it over and over again, every time we run this, we can also comment it out. To do that, you can do Control and then the question mark is a shortcut for comments. Otherwise, you can just put a hash sign before. So let's go ahead and jump into our demo. So we're going to start by importing some libraries. So we got quite a lot of libraries. Don't have to worry too much. We have some scikit-learn, causal next, and then we got PyEcharts. PyEcharts we use for our visualization purposes. So you go see that here, what we need to initialize some JavaScript for eCharts. And then
by the way, while we're in here, while we sent this these scripts out to you, we're thinking about creating AgileThought's thinking about bringing on board an open source community in GitHub, and that is putting a lot of our code that we develop, our scripts and our optimized models, Docker models, that we think are important to society. For example, you'll hear a little bit about the cancer stuff later on. Things like mental health models and stuff like that. We're thinking about open sourcing those models. That was work that we've done internally and just giving back to the world. If you think that is a good thing to do, and you're actually paying attention to me right now, I laugh at this sometimes because sometimes I think I'm talking to myself. If you think it's a good idea, please drop us a comment in the sidebar and just say, hey, I think that having an open source community would be awesome, right? Or it would be a good thing. If you think it sucks, say, hey, it's not worth anything. Just let us know, because your thoughts, you're our audience, right? And we just love to hear, and it'll have a big impact on how fast we move forward with that, if we move forward at all. All right, back to you, Arne.
Yeah, thanks. Yeah, we're really excited about the open sourcing of the data. So the data we have, like Dr. Jerry said, we have a breast cancer data set. So let's go ahead and get some of this data in here. So we're going to look at the breast cancer data set. One of the first things we need to do after kind of you glimpse through the data set is to remove unwanted columns. In our breast cancer data set, we're going to use all the features. So in this data set, we have a breast tissue from the tumor, and it goes through a lab as part of the biopsy, and they will examine the tissue from the tumor, and that's what these measurements are doing. So they're measuring the tissue from the tumor, and then they will diagnose it. So this is the diagnosis, malignant or benign tumor. And then these are the rest of the features. What the unwanted features that the feature that we do not want in here that has no relevance to our data set, it's definitely not causal and definitely not correlated, is the ID column. Who knows where it came from? It could be from the lab that gave it this ID. It could be the order of the patient. Who knows? So we're going to remove that ID column, and so we go ahead and do that. We'll select ID, and we're going to drop it. The next step is to turn our data set into or encoded so that we only have numerical values. Through Causal Next, when we do the structural learning to try to find the causal relationship, we work with only numerical values. So we have to take the columns, for example, the diagnosis, they have to be encoded into numerics. So we have a small function here, so we can do that quickly, and here you see the output. Fortunately, we only had that one column, the target column, the diagnosis, so that was fairly simple. The rest of the columns are all in numerics. The next step is to go ahead and select the target. So we want to separate our target from the our features. So we go ahead and do the drop down. You can select diagnosis, hit select, and we're ready to go. In Causal Next, we have to set up our structural learning. So we have some parameters here. We've already tuned them for you guys. So just go with a default. And then the final step in the structural learning is to fit it. So while this is computing that, we usually, well, not just us, in general, causality is split into kind of two main tasks. It's the finding the structural relationship, which is defined with a DAG diagram. So it's like a tree structure diagram. And once you find the causal relationship, you get how they're related and the strength behind them. The second part of in causality is to apply conditional probability, a Bayesian network on top of using the structure, and we can use that to further analysis, like do further analysis and do actual some inference, causal inference. And we do that, and we can actually go into more sophisticated stuff and something like counterfactuals. So those are the kind of two main parts of causality. So now that we finished fitting this, let's go ahead and start looking at the structure. So I've created here a function to plot all of our structures, and this is we leverage our E charts to do that. So let's go ahead and plot the first one. So initially, when you plot it, it's going to look really funky. What you see going on right now, it's kind of chaotic, things bouncing around. What the visualization tool has built in is a self-balancing kind of network. So it's trying to balance the distance between each node and try to make kind of sense of it, so you can kind of clearly see what's in there. But initially, when we plot this, there is nothing to see. Everything is connected to everything, and so what we need to do is apply some thresholding to kind of filter out, because everything is really kind of causal to each other, but we have to filter out only the important causal relations. Go ahead, Judea.
When you look at causality, when we look at causality, it's measured. One of the primary measures is entropy, right? It's a measure of energy, a measure of a relationship between. In theory, everything is related to everything, right? We've all heard of the butterfly theory, right? A butterfly flaps its wings in one part of the world, it causes a hurricane in another. There is a causal link, but not all causality is useful. It's all interesting, but it's not all useful to us. So what our goal is at this state, and this is what this is showing. Hey, and at some level, it's interesting. And by the way, if you study random theory, you'll come up with a lot of interesting kind of models, and you go, I had no idea. In this particular case, we do want to filter out those things. So that's the next step that Arnie's going to do. But it's just something to think about, that everything is interconnected. We are in an interconnected world. The question is where do we set those thresholds? Today, we're going to arbitrarily set them at a certain level in order to help you understand or visualize the value of this. So go ahead.
So here we go. Now we see our structure here. So let me zoom out to get you the whole picture. As you can see, now we have filtered out quite a lot, but the main focus is here on our diagnosis, and we have 4 main causal drivers into the diagnosis of the breast cancer. So we got the area, standard error, and then the fractal dimensional standard error, and then radius standard error, and then texture worst. You can also see that how these lines between them are the causal relationship, and they have a thickness, and the thicker it is, the stronger the causal relationship. So if you go, for example, into this parameter mean, you can see that it is much stronger relationship or causal to the compactness mean. So the parameter mean has a lot stronger causal relationship to compactness mean from the parameter mean for example. But this is really interesting to look at this of all the features that we have for this diagnosis. We can see now a map of how things are related and which one are causal to each other, and now we can start to better understand what is causing this cancer.
Yeah, and especially in terms of predicting its malignancy, right? And so that is where we can now have better conversations with the practitioners whose job it is to treat the cancer, which is if these are the characteristics that are actually causal in predicting the outcome of the cancer, what could we do to treat those things? We're not going to talk about that today. We're actually going to do something later this month on genomics in this area, but this goes from a bag of variables that we cram into a deep neural network and we go, oh, look at us. We just developed a great convolutional or recurrent neural system that has awesome prediction, to saying these are the things, these are the features that we should look at in terms of the priorities and how they interrelate, so that we can focus on a better and this is based on 1995 data, right? So the science that we make here today isn't in terms of, oh, we can come up with a classifier. The science we're making here today is we understand what's driving the classifiers. So let's go ahead and continue on so we can get through, we'll get through this and get their fingers on a keyboard.
Yep. So another, the second part of the causality, like I said, is to apply a Bayesian network onto the structure. So I'm just gonna skip that part for now. You're welcome to do that if you want to. You have this notebook. It is kind of straightforward, but instead we're gonna go and jump into the designer in Azure ML and actually build a surrogate model. That's a model we call is a surrogate model when you take only the causal features. So we're going to take those 4 features we have here: the area, standard error, fractal dimension, standard error, texture worst, and the radius standard error, along with the diagnosis, and build a classifier based on those. So let's go ahead and do that and jump into our Azure ML, sorry, the ML Studio environment. So this is our notebooks. Now we're going to jump into the designer. But before we can do that, let's go ahead and import a data set. So we need to import a data set. We're going to call it breast cancer. It's a tabular data. Let's get our file here. So it's parsing the data, getting the data ready. It found that it's comma delimited. It found that it has some header, so it applies the header. This is looking good. Let's go ahead and check it. It found the schema looks good. Let's hit next and just import it and create it. So now that we have created the data set inside our Azure ML environment, it now becomes accessible for all our tools and compute resources within Azure ML. So if you have multiple users, for example, working in this, multiple data scientists, analysts, then they'll all have access to it. So it's a really easy, good environment for your analytics and data science team to work in. So let's go ahead and jump into the designer. And we're going to just start blank. And normally we wouldn't have, we would just have these 2 data sets, but now since we input it into our data sets here, it becomes available to us. The first thing we have to do is to import our, or select the cluster. So let's go ahead and pick this cluster here. So, and then now we're ready to build our model. So we start with getting the breast cancer data set in here, you can right click on it. Once you drag it in, you can right click on it and hit the data set output. Microsoft has created this really easy and quick way to kind of have a quick look at your data set, and it actually plots up your histogram so you can see the distribution of each data set. So you can verify that if it's normally distributed or some other distribution you have. So you can have maybe make some changes to that column, for example. So here you see the data set. It is looking good. So next step is to go ahead and select the columns we're going to that are needed. So go ahead and select columns in data set. So what we're doing now is that we're going to select our target columns and then the 4 causal features. So so let's go ahead and get those again. So again, we had area standard error and fractal dimensional standard error. And then we have our diagnosis. And then we have the texture worst and radius standard error. And then we have it. So now we got 4 features and 1 target. All right, looking good. The next step is to split our data set. So in almost all machine learning development or model development, we have to split the data. So we do that to verify that the model we built is actually accurate. So we have to split our data set that we have into a test and a training split. So we'll just go simple and we just put 70% in training and then 30% in testing or validation. Then the next step is to train the model. So we'll go ahead and train the model. We need to get some actual model. So this piece here is only to kind of set up our target column. So we go ahead and select our target column, the diagnosis, and then we need to put an actual model that we want to choose into this training module. So let's go into the machine learning algorithms. We're going to go with a boosted decision tree, but we're going to do a binary classification. Since we're only looking at to classify if it was a benign or malignant tumor. So two class boosted decision tree. Why do we choose the boosted decision tree? Well, it's a tree-based makes it a lot simpler. We don't have to worry about scaling or categorical features, for example. There's a lot of forgiveness of using a tree-based classifiers versus. So instead of going into more details on explaining why, it's just we choose it because of simplicity. And then actually the boosted decision tree is quite good overall. The next step is to score the model. So let's go ahead and get the scoring. Where's our score here? So we're going to bring in 2 scoring modules. And we do that to compare our results from the training data set with our test data set. So like I said, we want to compare our results from a model and how we tune it, for example. We want to test it on how it does on classifying on the training set and then how it does on the test set. And so we have to get the scores for, sorry, this is the wrong one. We want to compare the training and the test sets. So we score both data sets, and then we want to evaluate it. So evaluate the model. And what this does, this module, is to, it's a really nice way that Microsoft developed the module here is to plot everything for us. It gives us the confusion matrix, which we can get the metrics out to see how well the model is doing. And you can actually compare two models. So you bring in your one data set and compare it to another. So this becomes a great way to kind of look at this module, the results, and this is kind of your reporting on how well your model did. So this is it. Let's go ahead and submit it. And then while this is, let's see. Let's get to run. While this is computing, I will then kick it back to Dr. Jerry, and we can kind of give you an intro into our next step in a workshop that we kind of want to give you guys ability to try out.
Awesome, awesome. So let me go ahead and see if I can manage this cut over here to send live. I think I've figured out what's going on with me. And that is, for those who don't know, I am a glutton for punishment when it comes to new technologies. And of course, yesterday on my production system, I decided to load the new Macintosh OS 12 on my iMac. And I think that there was a couple small bugs in this area, but we'll see. All right, so here's what we did. So Arnie, in 22 minutes, walked us through how we get data, walked us through a data source. I was good to close your window during demonstrations. So because the lawnmower people love to come by and chat with us at this time. So we went through from data source to bringing that data in, to looking at the data from a perspective of just general characteristics, descriptive characteristics, figuring out what's causal, stripping out those variables that are not of interest to us, keeping those variables are, going into the Microsoft world of model building and building a predictor model that we can score, and the result of which will become our digital surrogate. Remember, it has predictors. That's awesome. So now we need to get your fingers on the keyboard. Well, we're not going to do this particular environment. Our causality lab is going to be a bit different, right? And we're going to continue this particular example all the way through to the end. Another data set from UCI. This particular data set is from 2014, not too long ago, right? 6 years ago, and it has to do with the characteristics, the student performance characteristics of a South American school system. And in here you can see that we have a wide range of attributes that were collected. We had, as a function of how did they perform during their second, third, and final grades in this particular study. Now, here's the thing. I think all of us at our level have been through education, right? We either are parents or have had parents, and we pretty understanding of what really drives valuable education. So some of these attributes may not come as a surprise and others may. But what we're going to end up having a conversation on may blow your mind. So if we think about this, we have everything from the sex of a student. Was it binarily a male or female? What was the age? What was the address? What was the parental status, right? Were the parents living together or not? Interesting, right? I mean, think about measuring that attribute today. And we're going to talk about in just a little while about what variables you keep and don't keep. And some of these can be very politically sensitive. Some of these can be constitutionally prohibited in terms of segregating out of people based upon certain attributes, all of which though should be studied because it opens the door for conversation, right? Family size, reason, travel, failures in a previous class, right? School support. So we have all these attributes. And what you're going to do now is you're being asked, hey, can you help me? Can you help our school board, our school system actually improve overall results in the school, right? That's our goal as a team. We're going to, what policies and procedures do we need to put in place in order to improve the student grades within our system, right? So how are we going to do that? We're going to collect data, right? We're going to do the survey. Thank you very much, 2014, for giving us your survey data. We're going to figure out what of this data is causal, again, because we want policies and procedures, which means we want to change the world, not observe it. So the policies have to be changed, have to result in change. So we'll figure out what's causal. You're going to walk through that. Then we're going to go in and we're going to create a digital surrogate based upon these inputs, right? And then what we're going to do in the final phase, we're going to use evolutionary computing, genetic algorithms, to say under what conditions do the grades get optimized, and then we'll have a conversation about those parameters and what it means. And I think you're going to find some surprising things. So for right now, let's turn it back to Arnie, and you can now, we're going to slow down just a little bit, not too much, but just a little bit, and start to get our fingers on the keyboard, start to walk through this process. If you fall behind or you're not interested in doing it, keep in mind, this video, for all intents and purposes, will be available later on. You have access to the code, you can run it yourself. Whatever you choose to do today, I encourage you to do this exercise tomorrow. You cannot get good at this stuff if you don't get your 10,000 hours at bat, right? You have to do this work. You have to fail at this stuff, right? So I'm encouraging you to put your fingers on the keyboard today, tomorrow, next month. Fail at this so that your brain starts to help you figure out, oh, I now get this, right? And it takes people a little bit of a while to finally get the little light come on going, oh my goodness, this is the most important process I've ever done. I can change the world with this, right? That's what we're empowering you to do. So Arnie, let's go ahead and let's get the team into helping the school board identify the policies and procedures that need to be changed in order to increase the grades within our district.
Yeah, thanks, Jerry. On top of that, about getting work done, we've provided you guys with the workshop that you have access to for the whole day. You can also, I think there's a free access to Microsoft to sign up, and you can get free trial or something to Azure. And then of course we provided the notebooks, and you can just run it on your laptop locally. So you have it all. You can have access to it all, and so do the work. So going back to the data here, this is our notebooks environment. But as you remember, we were working on Jupyter Lab, so we're just going to jump into the Jupyter Lab tab over here. And so I had hid away the kind of like the files. You can either click on it here, or you can do Control B. And I just did it while we're looking at the data, so we get more kind of space to look at everything. So right now, we just finished the causality demo. Now we're going to go into the part A. So let's go and open that one. And let's go and start by importing the necessary libraries. We run the necessary kind of settings. So this setting here is just by default, I think Pandas, which is our library to visualize tables, just has a 10 columns to view. So by putting in this command here, we set the limit to show me at least 60 columns. Then this one here is just to load the JavaScript for our visualization library, and then we just declared an empty data frame. So next step is to grab the data. So we're going to work with the student performance data set. So let's take a look in there. So, and then, so here are the features that we have. The samples we have are 395 samples and 33 columns. So the rows are the samples, and then the columns are the features. I also have here included some text data file. So as you can know, we have this exclamation point here. That's to get into our underlying compute behind the notebooks. So if you are familiar with this cloud environment, most of them use a Linux. So I'm just running here a Linux command, a cat, which is to kind of spit out in the console the content of the whatever is in here. So I'm just in this Linux command, I'm just show me what's inside this text file. And inside the text file, we have here a description of all the features we have in our data set here, in our data frame. So this is what we call a data frame, and it's kind of like an Excel like view, and then all the data is kind of formulated like this, and we call it a data frame, both in R and Python.
And if you're a real data scientist, Ernie, those data frames actually are part of the R environment. So that's what I mean. That's where us real data scientists are not.
Right.
I'm just
sure,
joking.
the real ones. So,
right.
Going back to what Dr. Jerry was talking about, removing sensitive data. Like he said, for our purpose to kind of go through this data set, we've looked at it many different ways, and what we're deciding here is just to remove some of these columns here. But for the purpose of studying, you should not be limiting yourself to excluding any of them. You should try to include them all, try to understand, but for this purpose, we're going to remove some of these.
Little sidebar in there. Going back to the causal characteristics. So one of the books we recommend to folks is a book by Judea Pearl called The Book of Why. The Book of Why, W-H-Y. If you're interested in being a true practitioner or true connoisseur of causality, you really need to dig through his work, because he's the godfather of causality. He actually makes the historical case for it, why it's important, how the world would have been different, and then the math behind all this stuff. In there, he helps us understand the difference between statistically controlling for a variable. For example, we all see it, right? If you're involved with any kind of experimentation, we will statistically try to control for gender, right? Male versus female. Age, will bucket people into various groups, between 0 and X and Y and Y and Z. Locations, left versus right, north versus south. So we control for those variables. And why do we do that? Is because of the complexity of it. What Judea Pearl argues is, no. Understand the causality of it first, right? And in that space, once you understand the causality of it, you can make decisions. So I'd spend time in that area. That oftentimes will lead to some uncomfortable conversations. For example, why are we asking people in this study whether or not mom and dad are living together? Why are we asking people in this study what sex they are, right? Those are uncomfortable conversations. And the reason we're asking that is to get a behavioral understanding. Again, data is what? Slide 4. Data is the debris of human activities because of us, not in spite of us. If we can't dig deep enough into the behavioral into the data to flush out the behavioral characteristics that are causal to the concern, then all we are is reporting on the future, and we stand no chance of changing it. So in this particular case, all cases, you want to study everything and then exclude them later on when it comes to policy, right? Because of certain characteristics. But for today, we're going to make our life easy and get rid of some stuff. Back to you.
Yep. Thank you. The next step is, once we've excluded some of these columns, the next step is to do, like we did in a demo, is to transform our categorical features into numeric. So when you have letters and stuff in here, we want to convert it to numerics. Let's go ahead and do that and look at the output. So we go from U and R into 1 and 0, for example. So U being urban and R being rural. So now that we have all of our data here transformed into numerics, we can go ahead and start doing our processes. So right now, we are going to identify the causal relationship. We also call it the tree of life. And we're, again, trying to find the causal relationship between each column based on their value. It's based on mutual information theory, and it takes a while to compute, but then we'll be able to see the structure and the causal strings between each feature.
And by the way, for those who are not quite familiar with this environment, if you look into the upper right-hand side next to the thing that says Python 3, you see a little black dot. If you were observant, you'll notice that was a little circle before. And so the black dot just means, hey, I'm off thinking about your problem. Give me a little bit of time. When I turn white again, I am ready to go. So it's a little visual indicator. Tips of the day by Dr. Jerry Smith.
Great tips here. It is still busy computing. I will say here, kernel is busy. Also a note, there's another one here showing it. Another thing about
talk about that, but real quick on the tree of life, since we're waiting for it to compute and it'll come back. Yeah. You know, we give sort of unusual names to some of the items only to make them stand out, right? The circle of life, right? Hopefully you'll never, you know, the intent is for you to visualize that and say, you know, to change the future, to change life, what does that circle represent? Oh, I forgot to cover this. It represents a closed loop system, right? If you're a student of systems theory, which by the way, we don't teach anymore in most schools, systems theory, you'll find out that closed loop systems, stable closed loop systems, an important characteristic, because you can get unstable ones, but stable closed loop systems are self-correcting, right? When you say, I want to do X, and you go do it, and the world responds, and you measure what the world did, and you take the difference between what the world did and what you want, and you create an error, and then you course correct on that, wash, rinse, and repeat, it will self-correct. There's no plane on planet Earth that is perfect. Oh, we're back to this, and I'll complete the sentence and then we'll move on. No plane flies a perfect course. It's always self-correcting. So that closed loop system is a self-correcting closed loop system in there. And I'll come back later on. We'll talk more about the tree of life versus the circle of life now that we're done. Go ahead, Arne.
Yeah. Like we did in demo, I provide you here with the plotting function. So we go ahead and plot this. Again, like last time, we have a kind of chaotic, everything is causal to each other at some point.
Wow, look at that. That's awesome.
It
you
is
should
pretty...
sell that as a snap. It beats that.
I should turn it into a GIF and just have kind of, I don't know, running all the time.
Absolutely. You say the GIF should be, you wanted a model, here's your model.
So you can see here, it doesn't matter which one, they're all kind of causal to each other. So let's go ahead and remove some of these weaker causal relationship. And here we go. Look at that.
This is, and I always challenge our data scientists this. Anytime you do something, there should be a reason. We're not going to spend a lot of time on what the numeric value of that we're going to set, whether it's a 0.2, a 0.5, or a 0.7, or numbers not even in that spectrum. You should have a thought process for why that's important. And here's the neat thing, which is after you do this for a while, you can develop rules of thumb, you know, for 0.7, 0.8, those sort of things, getting rid of those pieces. But you should spend the time and ask the question, you know, as you think about the x-axis being the sensitivity factor, the filter factor here, and the y-axis being the number of relevant variables, right? Where do you set your number? Every model is going to be different. And the way you answer that in the future, and if you're interested in this, we can do this in a different seminar, is what we call sensitivity analysis, right? So the x-axis is the number of features, and the y-axis is the sensitivity, that is the change in those variables as a function of change in output. And at some point, you get this asymptotical curve that says, me adding another variable by reducing the sensitivity and being more inclusive only results in a smaller and smaller incremental return on the changes that could occur with the result of those. So at some point, you get to the butterfly. And yes, the butterfly did flap its wings, and yes, it did have an impact on the hurricane. But for our purposes, that value is so remote that we can discount it. And you should measure those things. You shouldn't just willy-nilly just set parameters on anything. You should always understand, how did I get to this number? What was my measure? Should I explain it? And then eventually in life like us, you'll get to a rule that says, hey, I'll just put 0.5 in there, 0.7. Yeah, this looks good enough, right, out of the process. You get lazy like we do. Go ahead.
So yeah, now we have the causal model. The first thing we kind of start to see right away is that we have the causal linkage between G1, G2, and G3. And this is the grades at semester 1, grades at semester 2, and grades at semester 3. And we can see that they're clearly causal or influential to each other. Some of the other interesting ones are, yeah, go ahead.
Real quick. The reason that is important observation is that should make us feel somewhat good about the model, right? You would think that if you were going to get good grades in semester 2, term 2, you probably should get good grades in term 1, et cetera, et cetera. It doesn't mean that the model's right. It just should give us a degree of empathy that this, you know what, I see that it's not wrong in that conclusion. It isn't that grade 1 is dependent on grade 3. That would be temporally inaccurate, right? There would be something wrong with the model. So we can get a good feeling about the model by looking at sort of customary structural and temporal boundaries that should not occur. And temporal boundaries are often the best way to look at, which is to say certain things tomorrow or certain things today can't be contingent on things happening tomorrow, right? That's what this is saying. We are temporally accurate. Go ahead.
Yeah, and then some of the other stuff that is really interesting here is that, so if we look at the semester 1 grades, so for that student, what are some of the causal features that play into him getting good grades versus poor grades? And one of the things is its address. And if we go and scroll up into our text file, we can see that the address is student's home address and type. So it's either urban or rural. So that's interesting. So that's a big contributor to a person's grade. And this could be something for regulars to start looking at and start to think, okay, why do rural or why do urbans get different grades? Or what are we doing poorly in urban or doing better in rural, for example, or vice versa? So this is a really informative graph that is going to help us change the future or change the outcome. Study time. Obviously, that's a big contributor. This higher. So higher is the students' willingness to go get a higher education, wants to take higher education. So if he's motivated to want to get a higher degree, or and you can see the strength of the causal relationship. It's one of the thickest, meaning it's one of the strongest causal relationship is with a higher. So having somebody that is motivated and wants to get a higher education, he knows he needs to get a good grades, so he's willing to do it, and that's one of the strongest pieces that goes into that person's wanting to get a good grade.
And if we look at how higher that degree has its impact on study time, right? As parents, we often say you need to study more, you need to study more, you need to study, and that's true, right? Study time The amount of time you put in onto your education has an impact. It's obvious, right? It shows it there. But what drives that even more so is this desire, right? So while we can preach to our kids, study, 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 right, and beat them over the head with the proverbial parent stick or policy stick, mandating things, what this is suggesting is that if we focus more on instilling a desire for higher education, that by its nature will then impact us and naturally impact a student's study times, which will then also contribute. Really important, right? I mean, this you can actually stand in front of a school board and say, yeah, I understand that you want to mandate study times, but the better thing to do is that less conversation, and here's why. And then have them say, oh, well, what kind of programs now can we put in to get people excited about higher education, right? Rather than force a horse to try to drink water, what you want to do is you want to lead them to the lake, right? Anyways, good stuff.
Yeah,
let's keep going.
Great stuff. Yeah. So now that we kind of did a quick view of our data set, one of the next steps in the causality is that we would extract the main contributors to the grade semester grade 1. So, and as we look at this data set here, we notice that we have numerals that are like not even related or not even causal. They don't show up on the graph. So we would go ahead and remove those, plot it again, and now that those things are removed, it's a much simpler, cleaner graph. What I didn't talk about before, I'm not going to walk through it, but I'll talk through this piece. You guys can go through it. Again, we created this structure here. So this is the structural learning, and the next piece that we would do in the causality analysis is to apply Bayesian network on top of the structure. So based on the causal relationship, we will apply conditional probability using the Bayesian network to be able to identify, so we can actually do some causal inference. So what does that allow us? How is that different than, for example, regular machine learning models? The main thing is that with machine learning models, you have features, you feed it the features, and it gives you an output. After you train the model, all you do is just the ML inference is that you have features, you feed it in there, and you get an output. What's different with causality and the Bayesian network is that you can actually go from the output and extract the features. You can go ahead and say, I have this output, I have grades for the student, but tell me what features and how much in those features should I change the value to achieve that goal. So we can go ahead and say, for example, a student comes in, we've had this causal model, and that student wants to go from grade, let's say it's from 0 to 20, he wants to go from grade 10 to grade 15. What does the student need to do that? And we can apply that with a Bayesian network, and it will tell us which features he should focus on and how much the value should he be working on. So this is this is the prescription that Dr. Jerry and I have been preaching on, that this is what businesses should be focused on. This is what's going to drive value. This is going to bend the curve. What we can do it with the Bayesian network, like we do in causality, and we can also do it the same way by building a surrogate model. So we take the causal features, we build an ML model with it, and then we optimize it over and over again until we find the features and the feature values that is going to give you the outcome. So 2 ways to do it. We can do it with a Bayesian network, or we can do it how we do it with deep neural networks, along with evolutionary computing, to optimize on a specific goal that you want to achieve. So that's the second, yeah.
Yeah, let's go ahead and move into the second part now.
Yeah.
Which is, I'm just quickly show what that's going to look like. And of course, I do think that this is a problem with.
Did you want me to build the model first or no?
We're gonna walk into that real quick. Let me just walk
okay.
into that with these slides here, because it's the only thing I'm capable of doing today is troubleshooting the Mac OS 12 environment, which is I always enjoy doing. Like I said, I'm a glutton for punishment. All right, so what do we do? We built a causality model before. Now what do we do? So now that we have a causality model, right? Now that we know what elements are causal related, again, why do we do that? Pause for dramatic effect. We do that because we want to change the world, not observe it. That should be one of the taglines that every one of us just adopts. My goal in life is to change the world, not observe it. So what do we have to do? Always figure out what's causal. Build your causal model, which you have those capabilities now. What we're going to do now we have that causal model is we're now going to say, I need to predict tomorrow. If I'm going to optimize it, I have to be able to predict it. So now we're going to move into Microsoft land. And Arnie's going to take this model that we built, right? This causality model that we have in here, and then build up a Microsoft Azure machine learning model that we can then go into the last phase and optimize. So with that, Arnie, go ahead and take it back over, and we'll work out that model in Azure land.
Awesome. All right. Cindy live. All right. Go back to where we left off. So, come on now. So we left off. I was talking about the graph. I ran through some steps that you guys can do later, but most importantly, we are going to look at only the main causal features to the semester 1 grades. So only those highlighted ones here. And then I've pointed them out in here. So we got that. We built this data set that we're going to just call data.csv. We're in the environment, the Azure ML environment. So I'm going to show you how to do it from the notebook now. Instead of going like we did last time, we went into the data set, we uploaded. Now I'm going to show you a different way to do it and do it from the notebook. So what we need to do is to kind of call our workspace. So we have a workspace name, we have a subscription ID and a resource group. And let's go back to the lab environment. And in here, we should have all the necessary information. So again, we have the workspace name here. So let's go ahead and copy that and paste it in here. We should have a subscription ID. Here. And then last, we should have a resource group, which is this one here. Now that we have that in place, run it. And then we can go and store this. So we will call this student performance dataset. So we upload the file that we just created in here in our notebook environment. And then we're going to take that from the notebook into our data store. So let's go ahead and do that. It's going to upload it. And then once it's uploaded, it's going to register the file. So now that it's done, we can go back to our Azure ML and we should see it in here. So again, yeah, now we have the student performance dataset. It's tabular just like we did with the uploader. And then we should only have those main features, the causal features. So let's go into, let's go into the designer. So Jerry, let's go ahead and build the model first, and then we can look at the results from our first demo. I think that's a good path to do it.
Let's get them building this model, and as its thing at the end, we can go back and look at the results.
Yep. So again, we have to, every time we start, we have to select our compute. So we're going to select our cluster here. It worked pretty well. It's pretty fast this time. I've learned my lesson to ask for more compute resources. So bring in our student performance data set. Again, you can go right click on it and you can visualize it. And we should have only those causal features. So total of 8 features. 1 is the target, the G1, and the rest, the 7 of them, are the causal features we identified. The next step is to bring in our. So we don't have to.
By the way, just real quick, if we go back, the data scientist brain is kicked in here. Go back to the previous, the distribution slides, please.
Oh.
Let's have some fun with this. Valuation, right? So as you know, as we're looking at this, as it brings up, and we see here, we look at the output, the G1. We notice that's not normally distributed. Question we may have in this space, is that important? Right? Is that an important? Should we transform that space to a normally distributed for some reason? We need to answer that. We don't have to answer that today, but anytime that we're dealing with data sets, the question about the viability of applying a specific operation or capability to it should be based upon its distribution, right? We need to do those things. You don't add. There are characteristics of distributions that prevent it from being applied to specific models. So one of the neat things about this environment is we can very quickly sort of visually get a feeling about the data. It's not normally distributed, so we may want to look at that later on. Just an observation.
Yep. So the next step is to, we want to bin our data set. So why do we want to do that? So as you look at the results, we can look at it as right now the data set we saw, the grades are numeric, and there's a continuous variable, meaning it's not a binary, but it has a continuous value in it. And to apply a machine learning model to it, we would have to use a regression algorithm. And just for simplicity, I'm going to go and bin the values into just 2 bins, either a pass or a fail grade, just so we can use a binary classification. And that only reason is just to get a better performance results, just so we can easily see a graph instead of looking at it from a regression where we kind of look at error rate, for example, so that it's not as pleasing to the eye to look at those results and doesn't have as intuitive results. So that's why we're gonna apply the binning. So we're gonna do from 0 to 10 to 20. So it's gonna put it into 2 bins, the fail and then the pass. We're gonna pick the column we want to apply this on, and that's the G1. And we want to make sure we're going to do in place. So I don't need to add another column in there. I want to replace it. Now that we've done this, we do the same thing. So last time we would select the data that was only the causal features. We don't have to do that. We brought in our data set and it only had the causal features. So the next step is just to split the data. So we're going to split it into test and training. Then we're going to get the training module in here. So let's go again and do 70%, 30%. We're going to feed it into the training module. We're going to select the G1 as being the training or the target, and then we're going to get an actual boosted decision tree classification, score the model, or score the data set, I should say. So we take the output from the trained model. So this is the training piece. We go ahead and train the model. Once it's trained, then we can take and do the inference on each data set. So again, the Azure ML Designer is a really intuitive way of working with the data in a visual pleasing way. It makes it really simple and really actually a fast way to build a model. And then if you wanted to do a repeat, you can actually use this as a template for another and just swap out the data set, for example. So it's a really intuitive way to work with and build ML models. So now that we've built this, let's go ahead and submit it. So now that we built it, we're running it. Dr. Jerry, it's back to you, or if you want me to show the results.
Let's go back and look at the results of that breast cancer fine needle aspiration, just so that we can see, the confusion matrix and stuff like that. Talk about that, and then let's build it. We'll come back and should have the results. So what does this tell us? Yeah.
So right now that the model has been built, has all this green boxes, mean is finalized, is done. So let's go ahead and view the results. Sorry, wrong. Visualize. So now that we've looked at, so again, we were only looking at the breast cancer data set. We had one target and 4 features. We started with 30-something features, if I remember right. And
right, which is the typical number of features that are used in most classification models for breast cancer. So we went from 30-ish, we went from large numbers of features, which are shoved into models for people, and narrowed that down to saying, by the way, these are the ones that are causal for a diagnosis of that, which have policy implications, have therapeutic implications. And we're now able to predict or classify an FNA based upon a smaller set. What is the results of that work tell us?
Yeah, so a little bit about this output window here. You got the left port, right port. So left port was the training set, right port is the test set. Nothing really shows the difference here, but when you scroll down, you can look at our confusion matrix here. So now we're looking at the training set, and you can see that we make 0 mistakes in the training.
But that's on training, right?
That's on the training, right? So we can start to see, yes, we are overfitting. We're pretty overfitting with our model and the tuning parameters that we used in this experiment. So looking at the test set, we can see that, yeah, we made few errors.
Okay, but this is a great conversation, right? Anytime you get a perfect fit in your training set, you most likely are overfitting. There are other measures for that we can examine, more statistical in nature rather than observational. But if we look at this, and we've had these conversations a lot, especially in the medical community, healthcare community, pharmaceutical community. There's one box on this 4-quadrant matrix that is the most important when it comes to this stuff, by far. And it's not the 99, and it's not the 157, right? The 99 says, hey, we said this was malignant, and it is. And it's not the one that says we thought this wasn't malignant, and it isn't, the 57. It's the one that Arnie's mouse is over, the 6. And this is the one that kills you. This is the one that says, we didn't think this was malignant, and it was. That's the one when the person walks out the door feeling comfortable in their life, saying, oh, good news is I don't have it, and then dies from it. The upper right-hand quadrant is the one where we've unduly stressed them out. We've said, hey, we got some bad news for you, right? It looks like you've got breast cancer. And as it turns out, secondary, tertiary tests indicate that that is not the case, right? Yes, they were high anxiety for a while, but at the end of the day, they didn't have breast cancer in this space. So we focus on how good are we? I mean, are we reasonably assured that we're giving positive results where positive results are doing negative results and negative results? But more importantly, it's in that 6. The question is we never want that to be a number greater than 0. You never want that. So do you do that through this model, or do you do that through other tests, right? So if we have that, if we know that there is a non-zero number for false negatives, what could we do to as secondary test or to improve the model? So those are conversations we would have later on. But this is not a bad model, right? Given the fact that we're only looking at 4 characteristics of the fine needle aspiration test in here versus the 70s. Of course, then that begs the question, if we add in all those other features that we discounted, would that improve the model? Of course we want to do that observation. But we're doing this from the standpoint of saying our goal then is to control the eventual diagnostic, which is to say, if we can control those parameters, we can control the potential diagnosis of malignancy. So how would I reduce or change those parameters? That's a secondary conversation. That's an optimization which we're going to get in with the students. Yep. Right? So these are, even if you don't deploy this, sitting down with the oncologist and asking questions like these 4 parameters, what pharmaceuticals, nutraceuticals, or genetic processes would affect these parameters in this particular measure? Because if we affect them, we change them. That's the important conversation. And you may find something. Anyways, good stuff. That's the good. This is, by the way, this is the part that excites me the most, which is this is when we AI machine learning data scientists folks get to use our words, get to use our adult words with the real important people in our lives, which is the people in the business side of the house, which in this particular case is the oncologist, right? The people in the treatment side of the house, which is the doctors, right? We get to sit down and instead of using the language of math, which can be confusing to a lot of people, we can use natural language and say, what affects this? What affects the surface area, right, of the things? Is there any pharmaceuticals that can reduce the surface area of this particular fine needle aspiration? And, you know, talking about the pharmaceuticals on that, or the nutraceuticals, nutrients. Those are great conversations. That's where we want to get to. All right, so let's go ahead and go into the results of the should be done with the other one, right?
Maybe. Let's go and see.
Maybe. I'd hate to have to dance some more here, but to go back to it.
Still training. It's close. It's on the last. It's much faster than we've been doing.
It's amazing when you put more than one wheel for the mic around. How fast it doesn't take 3 days to do this work. But while we're thinking about those conversations,
yeah, I was going to go with, and if I could add the notebook, our latest notebook, add one more library there, and then hopefully we'll be done then. So I just wanted to add here our deep library. So deep is our distributed evolutionary algorithms in Python. And oh, that was too quick. Anyway, that's done. So going back to you, Dr. Jerry.
Yeah. Let's go back to the model just to see if it's done, and if it is done, we'll evaluate it, and then we'll pop into the last phase here. All right. So while we're waiting for this, this is the preacher in me coming out. We undervalue the conversational aspects of data science, right? And that is more important, I think, than the actual results. And we're going to see this. Matter of fact, we can't see it yet because we don't have the results of this particular model. My suspicion is going to be this model may not, because we've done this several times, may not end up being as accurate as we want it to be. But that's okay. We're going to talk about that. And my point here is spending time with the business community on the implications of your work is only valuable. It's only valuable when you understand that the elements you're talking about are causal, will change the future, not observe it. Now you have a meaningful relationship. So what do we have here? What's our model tell us?
Yeah, you can see it is pretty poor model. You can see the blue one is the training set, and then the green one is, I mean, it is dangling around 50-50 with the test set.
Yeah.
So
yeah. So here's the thing. This is usually where a data scientist would throw this thing out and say, oh, this is a bad model. No, it's not a bad model, because we can have a conversation, and we're going to show this in optimization. So this is where I want to go back, right? Oh, by the way, do the actual, right here, there you go, and then go down to the truth table there, the
Yep.
confusion matrix, right? So look at this confusion matrix. It is confusing, right? The false negatives here, that is being able to say that a student is not going to do a good job and they don't do, and they actually, a student's going to do a good job and they actually don't do a good job, can kill a student, right? That's way too high, right? This model needs to be worked on. I cannot defend this model, but we're going to use it as an example of an important part of the process that we often don't include in our development work. Let's go back to the beginning, circle of life. What is the primary characteristic of that model? It is a circle. It is a feedback system. It says collect data, figure out what's causal, build a digital surrogate. We're going to go into the next phase of building a prescriptor, which is an optimizer. And then it says go into the field and implement those results. Go take a coffee break, relax, wait for a day, a week, a month, a year, collect new data, do the process over again. And because it's a closed loop system, that is, we finish where we start, we update the data with policy changes or changes to that result in new data characteristics. This system will self-improve over time. Now, do you want to self-improve? Do you want this system to learn how to fly an airplane and crash several times in order to get the right model? Of course not. You don't want to do that, right? We'll do it in simulations. Do you want people to die from cancer because you're experimenting, you're working on them to improve your model? Of course we don't want to do that. But understanding that the nature of this process is a stable, closed loop system. Over time, even if you have the worst data in there, causally it will cause the system to correct to the best data in there. That's the difference on this process. So we're going to keep going on this. I'm actually going to take control real quick here. I'm going to try again. I'm going to go with this send live stuff, and I know it's not going to work. So what I have to do is I have to X out of that and come in here. I'm sure this is a bug in the wonderful world of beta software. So go into here, we send live, there we go. All right, so we're now going to talk about optimization, right? So now what do we have, right? We have this digital surrogate, which is what everybody's talking about these days. I have a model that represents the thing in the real life, which means if I change the inputs, if I can change those inputs, we are going to get that output. If this was a salmon, one of my favorite, we haven't talked about that. I hate to switch metaphors, but it's one of my favorite models. If I go out into the world of European salmon manufacturing in 26 farms over there, and I collect data on salmon, I bring all that data in, I say, what's causal in that data to make a salmon fat, right? Over a period of time, I've collect feeding data, environmental data, water, moon data, phase of the moon. That's important, by the way, it turns out. What clothes I wore that day, did I wear black shoes, brown shoes, etc. I bring all that data in, and we say, okay, what is causal in making salmon fat? We'll figure out that what color shoes I wore were not as important as the fact that the phase of the moon has a huge importance on it. Why? Because salmon are feeders up. They look up, and when you have a full moon, you get reflective stuff, and they feed on that. So anyways, my point is now we build a digital surrogate. Inputs of the salmon result in it being fat over a period of time at a specific cost. So in this case, we had 3 outputs. How fat am I? How long did it take? How much cost? So I have a digital salmon sitting in there, and all I got to do now is to say under what input conditions, under what feeding programs, under what environmental, under what astrological conditions should I strive to produce or grow my salmon in order to maximize their fatness in the shortest amount of time with the least amount of cost. That's what we're going to do now with optimization. So when we get into this space, let me go over here, click here. Where are we? Click. Come on, you can do this. You can do this. Oh, if we click here, we think about optimization. So optimization does what? It takes our digital surrogate model, right, which is there on the left, and says, what factors do we want to optimize against? In our particular case, it's grades, right? But it could be grades at what cost? The school district doesn't have infinite budget, right? So it could be, what is the maximum grades I can get at the least amount of money? In the case of the digital salmon, my favorite example is how fat, how quick, and how expensive is that process. And then the inputs are all the things that we are causal. Now, the correlation stuff we've dropped out. I don't want to leave you thinking that correlations don't have value. And I often relate to the story about the surfer, right? A surfer doesn't create the waves that they ride, but if you give that surfer some training and allow them to shape their board, which they can create their board, they can correlate what waves they want to ride and do some amazing things, right? They didn't cause the wave, but they can ride that correlation into the shore and do some amazing things. So that's important, right? Now, a surfer would certainly like to say, hey, you know what? I can cause better waves, right? I can wait for the best wave, which is a type of causality. I can wait for hurricanes off the coast, so I'm guaranteeing higher and better performing waves for me to ride. So there's ways to shift correlation to causation almost all the time. But for the sake of the purpose, we do drop off certain things because, again, what's our purpose? To change the world, not observe it, right? We want to change the world, not observe it. So in this particular space, how do we do optimization? How do I search through all these inputs to this model that I have to figure out what of those inputs will maximize a single variable, multivariable optimization? How do I do that? Well, there's a lot of techniques, right? You can use things like statistical methods like Monte Carlo, right? Do a Monte Carlo analysis, which basically takes all your parameters on the input, randomizes them across their distribution characteristics, and then plots that as a function of the output, and then you visually or algorithmically find the maximum on that, and then the inputs that correlate that result can be derived from the curves on the input. Easy to do, traditional to do, very useful. Linear optimization techniques, you can do that mathematically. What we are going to do today is employ the field of evolutionary computing. And evolutionary computing has two branches to it. One is population evolutionary computing, or population-based, and the other is swarm-based, and let me just translate. Population-based, we've all heard from our parents, and they say, if you hang out with bad kids, you're going to end up being a bad kid, right? If you hang out with smart people, you end up being smart people, right? That's the idea behind population. And the rule is, you are the average of the 5 closest people around you, whether they're real people, or they're book people, or they're mentors that you have in life, fictional people that's out there. You are the average of the 5 closest people around you. So that's population. And what we do is we identify the value, we identify those things that have the characteristics we most want, and then we join them together, right? And think of that as the field of genetic algorithms, where we take the characteristics of a parent and 2 parents, and we blend them together through crossover techniques, and then mutate those in order to get some adaptation in it, and then we compare it and we draw new populations. So we grow smarter and smarter populations based upon those characteristics. Another field we are not going to talk about today is swarm-based, the world of Tony White, right, at Santa Fe Institute, in his book on swarm optimization, which says, if I get a large number of very unsophisticated things, think of ants. An ant has 10 to the 4th neurons, 10 to the 10th connections for each neuron, right? Pretty unsophisticated entity out there. It can't see, it can't hear. It has no central communications, right? The only communication it has is what? A pheromone. It leaves a trail saying, what does that trail say? Does it say, hey, let me tell you about tomorrow? No, it says, this is where I was. That's the only thing that trail does. It says, this is where I was. Now, if you take 10,000 of these ants, they can regulate the hive, brooding hive of an ant colony within 1 degree Celsius. How do they do that? called emergent phenomena. It's based on swarm theory. So swarm intelligence, taking unsophisticated things in large numbers that have a repeatable pattern or repeatable behavior, and that swarm then emerges unpredictably behavior. We're not going to do that today. That's very powerful. Today we're going to focus on using genetics to exploit positive benefits in our model, combine them together. And you're going to see some pretty interesting results in this. So Arnie's going to walk you through how we do that in one of many environments. This happens to be deep, right? The deep environment, we're going to show you how that works, but now we're going to take that model, you're going to figure out what are the optimal inputs, and then we're going to come back and talk about policy implications after that. Let's go ahead, Arnie.
Awesome. Let me go ahead and share the screen. Send it live. All right. So yeah, thank you, Dr. Jerry. Like Dr. Jerry said, we're using deep, the distributed evolutionary algorithms in Python. Yeah, what were you going to say, Dr. Jerry?
I was going to say I live to serve.
Got it.
Yeah. And by the way, would if we did this in R, would it be deer? Would this be a deer optimization rather than a deep? I'm just joking. Have fun at this stuff, man. Anyway, just joking, just having fun. God, if we can't have fun, why are we doing this? But back there on the wall, do what you love. Anyways, go ahead.
So first thing we do is to import some libraries, just like we've done in a lot of the notebooks. I like to get my width adjusted in pandas, import our data set. So again, we have the full data set we had in the past. And then we already identified the causal features here. So this is from our causal model that we developed in the past. One of the things that the evolutionary or the genetic algorithms or the deep library needs is to only work with numerical values. So again, do our similar process of transforming it. Then the next step is to create a prediction model. So we could, if we wanted to take the models we've developed, but we were working with classification models. So I'm going to change it a little bit. I'm going to use still a very similar, if not the same, gradient boosted decision tree, but use it as a regressor. So we're going to work with the values of grade 1. So again, we're going to work in numerics only. So we go ahead and run through scikit-learn. We're going to split the data up. 30% goes in the test set, just like we've done before. We're going to fit the data, and then we get some outputs here, which are going to be your R squared output. Then from there, we can see now we have the features from the causal features, and then we got the grades. Then to just kind of add to that, I'm gonna take this data set and apply our prediction model on there, and just give you guys the output from the prediction model, and only show me the top predictions. So the top predictions here have these features, and so that's the output here. So we got the grades here, and then we got the predicted grades from our prediction model that we created. So obviously you can see right away we're pretty off. I mean, we're way off here, pretty off here. So you can see our model is not the best, but we already saw that for the classification, and we're using very similar for consistency. We're using very similar algorithm, if not the same. Now going into the genetic algorithms, one of the first steps you have to do is to initialize our feature set. So when you work with generic algorithms, we have individuals and you have population. So we need to create those individuals, which is a student. So we have to take the features that we have for each columns, and we have to create a student. So for example, imagine you have this student here, 105, row 105. He has address of 1, p status 0, status type 4, for example. All those, we have to create those again. And they have address was either rural or urban, so it's just a binary. P status was, I think, binary too, but study time was 1, 2, 3, and 4. And the failures was 1, or 0, 1, 2, and 3. So we have to generate those things. And that's what we're doing here. We're initializing, just feeding the library or the model initialization steps. The fitness function is our evaluation function. That's our prediction model. That's what we're gonna feed into our features. The individuals we created, we're gonna feed them through our prediction models, and then our evolutionary algorithm is gonna optimize based on what feature inputs give us the highest amount of grades. And we know from the prediction model that's what's going to give us output for the grades. So these are some of the parameters. For example, some of the notable ones is here the selection model. We're going to use the tournament selection models. Other ones are like the roulette. Dr. Jerry can tell you a lot more about it since he's the expert in evolutionary computing.
But we're not going to go into that. The only thing I would say is, going back to my first observation, anytime you have a parameter you can use or change, you should always ask as a professional, why am I choosing it? Did I choose that because Arnie did it? Or did I choose that because Arnie did it and I know that was the right thing because of these reasons, right? So you want to spend time looking at those.
All right, and then the next, so now that we kind of put all our parameters, we initialized, we can take a look at some of the individuals. Here you can see
hold on,
a setup. Yeah, go ahead.
There's one parameter I do want to talk about because I'm following the screen here. Again, everybody, this is the first time we've actually done this live, right? We normally just do a slideshow on this and we talk about the possibility. We're actually going through it now, doing it live for this particular example. The one parameter I do want to talk about briefly is the population size, right? We selected 100, is that right?
That's correct, yep.
So the question is, why 100? Why not 1,000? So what does a population represent? It represents a pool of students with individual characteristics. This is population-based intelligence. Every genome, every string that's in there, this is based on John Holland's work, right? These are genetic string, represents a characteristics of a student who will result in some sort of performance, good, bad, or indifferent. So in there, and so Arnie set it up and said, I'm gonna put 100 units in there, 100 students in there. Well, why not 10? Why not 1? Well, if you have 1, you're only gonna get mutation, but why not 10 or 100 or 1,000 or 10,000? Well, the answer to that, beyond the scope of today, but I just want to plug this into your brain as an opportunity for you to go offline and do some additional research. It has to do with genetic diversity, right? And there's a lot of science to this. How big do my populations have to be to have healthy populations? You need to look no farther than your local zoo, right? In extreme species recovery programs, right? Where they're saying, we want to recover a particular species as being depleted. There are dynamics, there are models that say, here's the size of your population you need to have a healthy recovery, right? Especially with inbreeding and stuff like that. Genetic diversity is a key measure. So one of the key things we can do in measuring genetic diversity, if you scroll up just, there we go, I see it. As you look at each of these columns in that matrix, each column represents a value. In genetics, it's an allele, right? It's an individual element on a genome, right, in there. And by changing its value in genetics, we change a cell's ability to produce certain proteins, and those proteins then produce compounds, and those compounds produce you and I, or a donkey, or whatever it happens to be. In this case, that particular allele results in a certain activity that's going to happen. So what we want to look for is to make sure that we got healthy, normally distributed values. And if we look at that first column there, we'll see it looks like it's pretty good distribution, right? I mean, one would say it's a binary distribution, and I've got equal numbers of zeros and ones. In some cases, if you were to look at your results and they're all zeros, you would say, hey, you know what? Probably need to get some more allele diversity into this area in order to get this sort of genetic populations that will result in healthy and stable outcomes. So I say that as an intro to a future conversation, as in you're selecting numbers. There are mathematical ways for you to look at those numbers and ascertain, is my population size a healthy population for me to do what? To derive intelligence from. That's the question you want. This is the most important factor that you can deal with when dealing with evolutionary computing. All the other stuff is fungible, but this one here you need to spend time on. All right, so let's keep going.
Yep. So here's our main kind of loop. We have some plotting in here. We go through all the steps. I put in here kind of a picture of how the genetic algorithms will work. So we have the initial population where we have some features of individuals. We go through our fitness function, which is our classification of taking those features and getting a grade. So that's our fitness function. Once it picks the best ones from the fitness function, we go through some selection criteria. That's what we talked about. We use in the tournament. You can read on that if you want tournament selection in genetic algorithms. Then it goes through some mating where there's some thresholds or crossover points are selected, and then it starts to kind of mate those values together, or the features, and then it goes through mutations where we kind of swap bit inversion, for example, and then eventually we'll go through a generation. It goes through this loop and takes a new set of individuals over and over again, and we can set the limit how many generations we want to do. We set less than 1,000. So each generation is going to try to go as high as 100 population, and then try to find the most optimal set of random individuals through that loop, through the genetic algorithm. And then the outputs are here. It's kind of non-informative. The blue stuff here, that's the minimum. You can see it bouncing back and forth, but really quickly we just go right away and we are able to find the maximum, the global maximum output. So you can see here the best individual has a feature of 1032110 and has a classification of 16.612. This is interesting because if you remember right, I already showed you from the whole population, the maximum value from the population that we had from the classification we got is only 15.3. So
this is why we use evolutionary computing. There's two things. Number one is evolutionary computing is a form of quantum computing. It's a functional form of quantum computing. And what we mean by that is in quantum computing, it's the Schrodinger's problem, right? The cat's either alive or dead, and it's in both states until we observe it. Quantum computing allows us to compute in multidimensional space, and the factors only become relevant once we test them. And in what we're doing here, we're able to search an entire space, even though elements in that space were not present. And so what we did here is we created the state in which the optimization occurred. We did not discover the state. That's a super important difference in evolutionary computing. Evolutionary computing will create an optimal state based upon suboptimal parameters. So Arnie did a randomization of 100 students in a population, some which were not that well performing in the 4s and some were well performing in the 15s. But from that suboptimal set of students, we created an optimal student performance. That should blow your mind. We didn't discover it. It wasn't in the population. Hey, of the 100, which ones were the best? It was the 15. Is that pretty close to what we did? Yeah, of course it is. That's not the point. The point is we discovered it based on suboptimal results. Evolutionary computing is the only one that allows you to do that. That's why we use it here. And that's why now we couple this output, which we'll talk about in a second, with our process. That's why you can change the world. So what else do we have here?
Yeah, I just wanted to show, if we look at our data set and we try to just, all right, let's see in our data set which one had 1, 0, and 3. There's only 2 students that have this first 3 features, 1, 0, 3. And I mean, look at the results, 13.46 and 14.47. While the evolution algorithm found a better student, better performing one at 16.6.
Let's go back now and look at some of what those attributes for our optimal solution tell us we should be doing. So let's go back and look at that. So what was that first parameter again that we found? What was the result? It was a...
Yeah, one, that's the, sorry, address, oh, sorry. Let's go back here. So it was a 1, 0, 3. So address being, it's either rural or urban or rural. And then let's go all the way to the top here and find.
Yeah. You can never remember the values in this.
Yeah.
I'm
going to throw it up here in front of us here. Hold on.
And by the way, as you're doing that, let me just put the plug here. Remember, our model sucked, right? What was our model? It was like an R squared factor of
0.369. I mean, really bad.
You would do better with a coin flip with that model, right? So a proverbial randomization would do a better job, not necessarily a coin flip. But my point is this, is that we can still have conversations and then we can ask questions. What are we going to do on this pass, this version of the circle? Remember, that's the circle we're in. Which ones do we feel we can do now that we can implement, go back and collect new information and continue the work while we are building out better models, right? It doesn't stop the process. It just means that we are less confident in the entire outcome, and we want to be judicious in the policies that we implement until we collect new information and we go through the cycle. So what was one again? So one was
urban.
One was urban. So it was saying if you're more urban-based, urban versus rural, if you're more city-based, you're more likely to have a higher score, higher performing score.
Yep. The next one was P status.
Parental status.
Okay, let's go check what that meant.
So we want inner city folks. What else do we want?
Parents cohabitation status.
Yeah.
And then we got study time.
What was the result? What was the result of that? What is the optimum model say we should do?
That's right. It said 0 for the, so that means A. Okay, what does A mean in that one? T for living together and A apart.
So let's just think about what this model is telling us right now. We just said, in order for us to optimize our student grades, we want to live in the inner city and have parents living apart. How would you like to stand in front of the school board and make recommendations to get all parents to have a divorce and move the students into the inner city? So there's something in here that's interesting, right? And while we're not saying that you want to split parents up, what it's saying is because it's counterintuitive to us, we've always been brought up to believe that a family unit of parents is often better than a non-family unit. This strikes at the heart of that. And what this may beg us to look at in this particular case is what are the characteristics of the family unit in this particular part of the world at this particular time compared with family units that have mother and father separated, right? And I think we know that under certain environment and certain family conditions, they are dysfunctional in nature and could lead to hostile environments. And this may be a characteristic of that. Don't know, it's worth a secondary study. The other is the rural versus urban, right? Are we going to go out in the world or into the city? And this, again, if we go back to the causality model itself, may be an indirect indicator of proximity and travel, and how much are students spending the time on the road versus the time in class. All these things come together. So we would pull out that causal model again. We would start to take a look at the characteristics of how these things are laying out, and then have those conversational pieces, which is things like, let's take a look at how our families in our community are affecting the learning process. Do we have a hostile family condition where parents splitting up can control this factor? Are students coming from rural areas which are more family oriented but traveling in because they have to travel into the city for this and it takes them more time to get to school? Those are the conversations we want to have.
Yeah. And
even with
the last part
model
is our model is poor, so it could well be that
Could be.
it is failing on that particular feature.
Yeah. And what was the last one? Study time?
Yeah, study time. So that's 1 through 4. No, 0. So 1 being less than 2 hours, 2 being 2 to 5 hours, 3 being 5 to 10 hours, and then 4 being more than 10 hours. So it said 3, so 5 to 10 hours is our sweet spot here.
Optimal results. That's which is consistent with expectations, right? You don't want to just put no work in, and you don't want to dedicate all your entire operational time as a child, right? Child need to have other things to be healthy, right? Good outside activity, all that wonderful stuff we talk about. So it's consistent with that. Even with a poor model, we can have interesting conversations from which we would then implement policies, wash, rinse, and repeat the process, and see this stable closed loop system converge optimally to a set of students, a population of students whose scores improve over time.
Yeah.
Right.
Then we had a 2, 1, 1, 0. So
that's I don't think we need to go.
Yeah.
Yeah. I mean, so let's take a step back now and think about what we just did today, right? Real quick, and then we'll summarize it up and figure out where we actually go from here. I think that would be a good next step, right? We actually never did this before, so it's not like we know where to cut this thing off. We can go on forever. I mean, this is the problem this is the wonderfulness, I should say, of where we are right now. Is your brain should just be bouncing all over. Go, well, what if we did this as a policy and that as a policy, and who do we talk to? By the way, why did the parental status have such an impact? Should we do another study on that, right? Is that worthy of another study? Can you bring out that causal model again? Was there anything impacting the parental status? What was causing the parental status? And do we control for that factor? Now we're talking board level language or business level language to our customers, in this case, the school boards, in ways that they get value out of it, because they know that the policies they're going to implement based upon these variables will change the outcome of the students' lives. So that's where we start. That's where we summarize up. We talked about the circle of life, right? Step 1, grab your data. Data is a degree of human activity. Step 2, figure out what's causal. Not all data is important, although you may collect it. The ones we're interested in is what is causal to your business concern, the fat salmon, the smart student, the characteristics of breast cancer and non-breast cancer. We then take that causal data, we then develop a predictor for it. How does it change in the future as a function of changing the causal inputs? Why do we do that? We want to change the future, not observe it. Then we ask the question, under what conditions do I achieve the maximum benefit of the business problem that I was trying to solve for, the output? And we can do that in a number of different ways. We can just guess at it, just plug in the numbers by hand, or we can use evolutionary computing that will create the outcome that maximizes that benefit, because it's a functional quantum computer. We then take the results, no matter how bad the models are, the two models, the causal model and the digital surrogate, and after it's been optimized, and we have conversations with the business people. We say, what does this mean to you? And what policies, procedures, what sales and marketing if you're in a product or service company, what treatments if you're in healthcare, what pharmaceuticals, nutraceuticals, genetic characteristics do we need to do? If you're in insurance, what services could we put in place that would affect that? And you'll often find that you're going to need to bring new partners to the conversation, oncologists for healthcare, psychologists, sociologists for services oriented, especially if you're trying to get people to change their behavior, right? In that area, you need to actually spend a lot of time on that. If you, by the way, my plug for that is the book Nudge. If you haven't read Nudge yet, that's a lot, has to do a lot with the psychology and sociology of incremental change from a cognitive perspective. Go look at that book. And then once we get those policies and procedures, we go into the field and do them. And then we wait, right? A day, a week, a month, a year. And we take that data back and we start the process over again. And because it is by definition a stable closed loop system, it will converge on a optimal result, which means you change your company. You change your world, you change the business. You're not a bystander observing and reporting it, like so many data scientists are relegated to do these days, as so many CEOs wish that they could change, right? They don't want to sit there and just observe their competition. They want to change the dynamics. This allows you to change it in this spot. Very, very powerful technique. Any words on that before I go to our last slide, Arnie? I'll take while you're.
No, I think this has been awesome. We're excited.
Hey, listen, we make science news, right? I'm doing my thing. I have to go through my stupid process of selecting my slides again, coming up into here. There we go. Again, we science news, finite needle aspiration, or fine needle aspiration, right? 1995 data. You can't get anything new out of that. Of course you can, right? Student data, 2012 data. You can't get anything new out of that. Of course we did. Matter of fact, we took that to the ultimate level. We optimized it. We can have conversations. How many school districts in the United States, in Mexico, in Canada, in Europe at large, any school district on planet Earth, would love to have a group of people stand up in front and say, here's the changes that we want to make, and here's why it's important for you to listen, because it's causally driven, and if you do these things, we'll guarantee you'll change. Every student board out there will be, right? Yeah, a student board. All right, so carrying on here to the last couple slides. All right, so next steps, right? You are now, this is my superpower speech, you are now a superhero. You have a minor superpower, actually. And you may be thinking to yourself, oh, that's stupid to think about that way, but you do. You've now been endowed with an emerging ability to change the world through this technique. I'd ask you, what are you going to do with it? Are you going to sit back and let the world and just observe the world, or are you going to try to change some aspect of it? Whether it's something in your personal life, something in your company life, something in your social life. How do you apply these techniques, which you can do? Anybody that listens to this is able to do these things. What are you going to do to change the world? Because you now have a responsibility to the world with these powers to do it. I personally am looking at things like mental health issues and addiction, right? Substance use disorder. How can we help the young men and women that are dying every year, 75,000 of them, not die? Veterans, 17 and a half blow their brains out every year because of mental health issues. How can we reduce that number, right? Things like that are very important to guide people in my community. So how do we apply this process? If I say I can change the world, can I make the following statement? I will put this in place to reduce that 17 and a half to 15 to 10 to 9 to 8 to 7, 1, 2, and 0. If you're telling me, Jerry, you can change the world by identifying the characteristics of suicide, and we can put programs in place to identify those characteristics and intervene, then why aren't you doing it? That's what I need to do. Suicide from or overdoses from drugs, that sort of stuff. Relapses, breast cancer, all those things. Ask the question, what are you going to do with this? So that's number one. Number two is feedback. Love to hear from you guys. If you're online with us today, or you're in the future listening to this as a repeat of the workshop, send us an email. Send it to jerry.smith, right? And I'll respond to you. Let me know what your feedback is, right? tell us not only how we did, but also what could we do, right? We finally got through the optimization stuff, which is kind of fun. We actually have an end-to-end cycle now to show, so we're pretty happy with that, and we're going to continue working in a number of different fields, and I'll talk about those in a second. But tell us, what would you like to see, right? Would you like to see more of X or more of Y? And then let me just go on to the next slide here, which is our upcoming events. Where are you? Oh, go ahead. There we go. Upcoming events. We have some upcoming events. We have some cloud migration stuff coming up in July. We have we're starting a podcast, and you're going to go, oh my God, not another podcast, please, not another podcast. I'm tired of, there's an infinite number of these things. Well, there's one more, and this podcast is called AI Alive and Unbiased. This podcast is, I think, a bit different. At least that's my intent, and my heart says it's going to be different. And what we're trying to do here is we're trying to help bring these AI experts and the impact that they have, this actual people they have, impact on people, to light. So here's an example. In my heart, this is the one I'm really working for. We're going to take this journey together. Every show is going to be a bit different, but the one I'm working for, just to give you an example, is in the world of artificial intelligence. We are now able to take things like MRI, functional magnetic resonance imaging of the brain. We're able to create deep convolutional and recurrent neural systems that can translate those image characteristics, those sensory, that data that we collect, into approximate images that we're seeing in our head. Pretty cool stuff. Still at the really core stage. You show somebody a picture of a goldfish, you ask them to think of a goldfish, lo and behold, you can actually see images that look like a goldfish. I mean, it's not high fidelity stuff, but you go, that's a goldfish. That's interesting, right? Then you ask the question, well, what impact, what outcomes, how is that changing the world? Again, my role is I'm all about changing the world, not observing it. So how did this change the world? Well, here in Philadelphia, we have a mom who's been going into her son every day for the last 10 years, who's in a coma, and she's been reading. Why do we read to our comatose family members? Because we believe that it has an impact. We believe they hear us. We believe that it's healthy for the brain. It provides stimulus, etc. Right? A lot of studies show that to be true, but we've never had a chance to really look inside the brain. And so with this technology, one now has an ability, as you're talking to them, to have get a perspective on what are they thinking while we're talking. Is there somebody there, or is there nobody there, right? Has an impact. So the idea behind AI Alive and Unbiased is we're going to bring you these characteristics of AI, machine learning, data scientists. We're data science. We're going to bring you the experts in the areas just to talk about it. Has nothing to do with AgileThought. These are not our projects. It's me having a technical scientific conversation with smart people, and then going into the field and having conversations with people whose lives have been impacted by the things that we talked about. That's AI Alive and Unbiased. All right, the last thing is somewhere in the end of June here, we are going to do the AI and cancer, AI and oncology. And this is an important one for us because we did take a look at the Netherlands Cancer Institute's data on breast cancer. And this is actually different data than we looked at today, and this has to do with data associated with the genetic implications of breast cancer. There was something like 64,000 instances or observations across 295 women across, 65,000 genes across 295 women, which span lots of data. And we asked the question, which genes are causal to breast cancer relapse, right? Get breast cancer, you get treated, you go into remission, X amount of time goes by, you often relapse or you pass away. And that length of the relapse period is measured typically about 10 years. And we asked the question, of all the genes that you studied, which ones are most likely to affect that period of relapse? If you can take 10 years and make it 11, would that be a good thing to talk about? Yeah, I think so. How about 12 years, 13, 14, 15, et cetera? Well, in the industry today, there are 70 genes, there are 70 genes that often are being examined as a function of that relapse period. We found 4 that are causally related in a very similar fashion that we did with the breast cancer fine needle aspiration diagnostic work. we took that massive space of 30 and reduced it to a handful. In this particular case, we took that massive space of 70 genes and reduced it to 4 that we believe are more causally related to the relapse rate than anything else. We're going to have that conversation. We're going to actually walk you through that process, show you what we did. We're working on bringing on a geneticist to the project to actually talk about the implications of the genes from a pharmaceutical, nutraceutical, or genetics perspective, what can be done, and we'll have that. That'll be a 45-minute conversation. Anything else, Arnie, that we should cover before we let everybody go?
No, I think you covered pretty much all of it.
All righty. Well, listen, Arnie and I really appreciate you being here today. If you're watching this in review, it's still relevant. We encourage you, whether you're real time or in review, to get your hands dirty in this area and do this stuff. If you actually got to this spot in the process, in the recording, as I mentioned, you have a superpower, albeit minor, right? At this stage, what are you going to do with it? You're going to change the world or observe it. And that's what Arnie and I would like to leave with you today. Anyways, everybody have a good time. We'll talk to you later on. See you on the other side.